Welcome everyone to the WERA 103 presentation today. My name is Rob Mickelson and I'll be hosting the event. We're pleased to hear from Dr. Robert Flynn today. Let me give you a brief introduction about Bob. Bob received his bachelor's and master's degrees at Colorado State University and then his PhD at Auburn University. Bob's currently on the faculty of New Mexico State University in the Department of Plant and Environmental Science. He's also the superintendent of the Artesia Science Center, which is located in southeastern New Mexico. I know Bob from his activities as doing educational outreach, where his passion really is using science to solve real-world problems in agriculture. So it's a pleasure to have Dr. Robert Flynn talk to us today about high pH and some of the issues that poses in Western North America. So welcome, Bob. We're glad to have you join us today, and let's get you set up with your slides, and then you can go ahead and begin.
Well, thank you very much. I really appreciate the opportunity, and we will get going. So Western pH, it's definitely on the high side in most areas. It's a common problem out here in the West. We have high pH, of course. We have what's a lot of the locals call caliche, or your limestone type horizons that you can see in here, and that's going to dictate a lot of what our pH looks like. We also have to deal a little bit with salinity, as well as some sodicity and compaction, like a lot of other places, and of course low organic matter. With limited rainfall, what can you expect? So really, what is pH? A lot of places would tell you that it's soil reaction. So soil pH is soil reaction. Or is it an acid, or is it a base? It's another terminology that people use. We use a scale from 1 to 14, with 7 being neutral. It's neither an acid or a base at that time. And if it's less than 7, we consider it to be acidic. And if it's greater than 7, it's considered basic. Here's some examples of just different common things that we could associate with the pH scale. So we have our neutrality. Milk is pretty on the slightly acidic side, but more likely neutral. The battery acids that you have in your cars, it's extremely low. Lemon juice is very low. Vinegar, it's always a good experiment that I'll show you in a little bit about how to tell if there's some lime in anybody's soil around these parts. Rainwater, after that first rain, at least in this part of the world, we can expect it to be slightly acidic. And then we can move into the basic pH readings, where we have milk of magnesia, baking soda, seawater, ammonia, lye. These sorts of things are going to be on your basic nature. Now, what I really want to point out too is that plants actually have a very wide range of tolerance for growth with different pHs. Now, of course, there's several plants that prefer acidic conditions, and there's plants that will do very well in basic conditions as well. Those are the ones that we want to train people on so that they have success. One of the biggest aspects of pH is that it does control some nutrient availability to plants. So looking at this graphic, a common one that's found amongst the literatures, is showing the availability of like nitrogen, which is pretty much not affected until you get to very low levels of, and then phosphorus on a general scale is basically really well available in that 7 range. And then as we increase in the basic direction, we lose the availability of that phosphorus, and then also in our acid soils, we lose some of that availability. Potassium, not strongly really affected under the basic conditions, but we can lose a little bit of activity of potassium in our acidic soils. Sulfur, again, similar. Calcium, similar. Magnesium, similar to these guys. It's a poverty, I guess, for the Western region in that we always seem to be struggling with our micronutrients, and this is because of the pH. We have iron that as it goes above 7 starts to become less and less available. Manganese the same way, boron after 7, and then copper and zinc are also difficult to keep in availability for our plants. Molybdenum, on the other hand, is much more tied up in our acidic soils, so normally haven't seen anything related to molybdenum in these parts. So a lot of folks, they want to go ahead and try to mitigate that base. They want to add something. A lot of folks know that if you add an acid to a base, that you're going to get water and salt. That's the end products of it. And we can neutralize acidity by adding a base, or we can neutralize a base by adding an acid. In this area, of course, we're going to be trying to focus on neutralizing that base, and a lot of folks do want to add that acid. One of the, just a way of thinking about it, if you're going to clean your car battery terminal, what is it that you're going to use? Some folks will say Coca-Cola. You know, you pour a bottle of Coca-Cola on there and it's just going to clean it right up. But it might work that way, but does it actually neutralize the pH? Well, no, not really. Coca-Cola, it's an acidic product. If you want to neutralize your acid from that battery terminal, baking soda, a base is the way to go. So a lot of folks, once they start getting associated with the soils here, they would like to change it. So I was curious at one point just what the differences in our pHs would be based on a cropping system. And what I found through a replicated study was that cotton being an annual crop, the pH of the fields that we had averaged 7.4. But for our perennial pasture grasses that had been in for several years had lower pH. So there's a lot going on in these soils that deserve consideration when we're trying to manage our pH. Another way that folks would like to lower the pH in our soils that are low in pH or high in pH is with elemental sulfur. The general recommendation is for sandy soils, you would need 10 pounds per 1,000 square feet of elemental sulfur, or for a loam, a higher clay content soil, you would need about 40 pounds per 1,000 square feet. But wait, if you add an acid to a base, what do you get? Salts and water. Is that going to be more deleterious by our efforts? Well, one of the things that happens in New Mexico is that all these soils with lime, which is a very big majority of them in our ag lands, are buffered. And that means it's just something that's going to prevent change. Our water in New Mexico is buffered against changes in pH by the presence of lime. And of course, lime is calcium carbonate. One of those quick tests that you can do is just to actually use some vinegar. And a simple test is to just pour that vinegar out just a little bit on the soil. It could be dry or moist. And you can see that by adding an acid to, in this case, the soil, we start to see effervescence occur. And that guarantee then that you have a high pH. A lot of folks would like to get rid of that and start lowering it, but again, by doing that, you're going to increase the chances of too much salt being left in the soil. So if it did happen, then flushing it with water would be helpful. It's also an issue when we get into using our water, because a lot of our waters in the West have calcium carbonate in it already. And what we find our drip irrigation growers doing, such as on our vineyards, we have to be careful to make sure that we're treating that water to keep these at their recommended delivery rate. Otherwise, they tend to seal it up. The calcium carbonate seals that emitter off and it doesn't deliver what it's supposed to. There are treatments for that, of course, and that would be a good topic for another day. So how much calcium carbonate is in our soils? Well, if we have just 1% calcium carbonate, then that's 460 pounds per 1,000 square feet in 6 inches of soil. And if you're like us in this part of the world, in southeastern New Mexico, we have close to almost 7,000 pounds per 1,000 square feet of 6-inch deep soil. So if you really wanted to change that, the 1%, yeah, it's really not going to be too much of an issue. But once you get into these higher calcareous soils, then it's just a problem because of the fact that once you start to neutralize it, you're going to have issues with salts. That can be managed, but remember that a lot of our waters have calcium carbonate in it, so we're adding it as well. I did do a survey around the state, and what I found is represented in this graph. On the left-hand side, we have our soil pH from a saturated paste extract, which is my preferred method to evaluate these pHs. And we had the soils tested for the soil lime or calcium carbonate content. What I thought was interesting was that most of our labs are evaluating from 0, 1, 2, and 3% lime. And we can see that we can have a large variation in soil pH when we have calcium carbonate contents that are less than 3. But as we go higher than 3, it looks like, anyway, from all the sites that were tested, that we had a lot, anything above 7.5, all the way up to about 7.9 for the saturated paste. So it's always recommended that we do our soil testing with the saturated paste so that we get a good example or a good reading as far as what the pH actually is in our soils. The web soil survey also can be used to estimate your calcium carbonate content potential. Take, for example, San Juan County in the northwest corner of the state, can vary from 0 all the way up to about 8%. Now, of course, it's always beneficial to submit a soil sample from the location that is being used to grow crops or gardens or whatnot. In Chavez County, which is in southeastern New Mexico, on the other hand, we can go from 1% in some areas all the way up to 28% in other areas, with the most of it being in the 5 to 6% range. 15% is also common in other areas of southeastern New Mexico. The web soil survey can also assist. These are from 1-to-1 extracts for pH, so it'll be slightly off, but it is a good way to understand just to some extent about what these pHs are like in any given region of the West. Very good place to start. Now, one thing it does for our region, we have a lot of pecans in the area, but these high pH soils tend to promote deficiencies in our metals, like we saw earlier. So this is how pecan responds to high pH. We have a rosetting of the growing tip, and we have necrosis setting in a certain pattern for these types of trees. So micronutrient management is very important, and the form and amounts are important when it comes to managing these sensitive trees. There's a lot of homeowners that grow different types of trees and crops or plants that do not do very well in their area. It ends up getting iron deficiency. This usually is a result of a Lyme-induced deficiency, and there's many of those that are planted, but not for long. The joke is that eventually iron will kill the plant in the form of a chainsaw. But other plants that are grown for feed or for harvesting, they also can develop necrosis or iron deficiencies, and we need to be able to help these plants out with the addition of selected fertilizers, iron fertilizers. Strawberries. Now, this points to one thing about plants. They all have the different varieties, and there are varietal differences between their ability to withstand the lime content of our soils. So we had a study in northern New Mexico, and only 3 varieties are shown here, but we have Brunswick and Chandler and All-Star at 3 different times after application of the product. So from August 2nd to the 25th, and then at the end on the 7th of October. What we see is at the very beginning for Brunswick, it was a good plant. Didn't really have anything going on. As we go over time, we have a good product all the way down, which I would say this is tolerant. This is a type of strawberry that you would like to grow as long as it still has a good taste. Now, as you go to the chandler, you can tell right away that it has some very distinct issues, but after treatment with a chelated iron product, it started to recover. And then by October, we still see some recovery and still some evidence of having deficiency symptoms. And then the other product, or the other variety, All-Star, it had very bad chlorosis here. And by the end of August, it started to look like it was going to recover. And then by October, it actually did kick it into gear, and we had really good performance of that All-Star from the use of a chelated iron product. Now, this chelate is an iron EDDHA, and it seems to be one of the more better materials to use. Not necessarily everywhere, but it did work for this place. Homeowners, also roses, they can get it. What you'll see is that bright yellow leaf, a network of green veins that can actually turn white, as we saw even on the strawberries. The outer edges can scorch, and eventually you get dieback, and it just will not recover unless we put some additional iron into that mix of the soil. Now, folks that want to actually plan ahead before they purchase things in the stores or from seed dealers is to figure out, okay, once I know my soil characteristics, where can I go to get information about specific plants and their tolerance to pH? So the National Plants Database is a very good place to start. And then you can search on either the common name or the scientific name. And that can help you narrow down. And then you can start looking for specific varieties that might be touted at being tolerant to this type of a high pH situation. Well, there's also a lot of products that are fertilizers that are added, and we can look at iron from an iron sulfite point of view. That can be used. It's sold as copperas or ionate or Bandini 7 iron and even ironite. Ironite is starred just because it is a product of the smelting industry, and we're not really sure exactly if it's the best form with the other metals that are inside that product. The elemental sulfur can be added with iron sulfate, and that can help. And it can react then with the lime to help neutralize it. These are very simple procedures, typically a slow response to the product. It is usually inexpensive, but like I said, ironite has other heavy metals that it's not always recommended for general use. Now the chelates, on the other hand, there are different types of chelates out there, and there's been some work done on these chelates. They are, by definition, molecules that hold metals like iron, zinc, nickel, others. I just used the lobster because the molecule is like a claw, and it holds on to that specific iron or other metal in the structure of it. So we have hampine as an EDTA, and there's a DTPA iron product, and there's a EDDHA chelate. The Miller's Ferra Plus, that's just a trade name for it, and it can be found in other names, but you're looking for this on the label, the EDDHA. So how does it work? Well, these chelates performed in the following way. If you have the percent of chelate with the iron on it, and since some of these products like EDTA are sensitive to the pH of the soil, it is a very good thing to know what that pH is of your soil. So we can see that by the time you get to about 6.5, 6.5 with the iron chelate of EDTA, we start to lose about 20% of its iron. As we go up to near 7.5, we have very, very little. Even at a 7 pH, we have less than 20% of that iron still available to the plant. It's been used up by the clay, by the reactions that occur in the soil. And by 7.5 and above, we do not see any benefit for that particular chelate. So it's just a chemistry type issue with that product. Now DTPA, we have the blue line coming across. It's available all the way up through 6.5. It starts to lose a little bit at a little bit above 7 pH, and then it starts to be less effective as the pH increases towards 8. Once it reaches those high levels of pH, it is going to lose most of that effectiveness for providing iron to the plant. By 8.5, it's totally gone pretty much and does not do the job that it needs to do. So it's important to know that pH. The saturated paste pH is important. You get a slightly different number. I think that it's a much more reasonable number to use. And then finally, the EDDHA product is not sensitive to pH, and it has its availability is good across the pH spectrum. So a very good product. Of course, anything that good is, there's a price to it, but it can, a little bit goes a long way, and it's up to each individual operator or farmer to actually consider to use. Excuse the petunias in the background, but they are also very intolerant of high pH soils. But of the other test that was done in New Mexico on these products early on showed with sorghum on a very high pH soil had a test where they put the 3 different chelates out, and you can pretty much tell that with 2 parts per million of EDDHA, you start to see a response in yield. So this is a pot study for sorghum, and the iron DTPA and EDTA just haven't really kicked in until you get to 4 parts per million. You see a small increase in growth from the sorghum, but not nearly as much as that iron EDDHA. And you can go on up to scale up to 8 part per million of iron added, and you see that at the EDDHA, you're reaching a maximum, and most growers would be probably happy with using a little less, even down to 4, compared to what they're getting with these other products. So even at the DTPA, at an application of 8 part per million, that pH is just too high for it to have full effectiveness. So it does matter for our fertilizers what they are. Some folks also see improvement after adding manures and other products that are organic, get them to help to do that, do a better job at providing some iron. But there's no data right now that I can share on that. The results are usually fairly quick. This is a 4-day difference between an untreated and a treated